Hi, my name is Josh Grochow from the University of Colorado Boulder. This is my talk for CCC 21 on P-group isomorphism, joint work with Yoming Chow from the University of Technology, Sydney, where we get search to decision, counting to decision, and nilpotency class reductions for P-group isomorphism using tensors. So to start with, the group isomorphism problem is given to finite groups, G and H, and in this talk we'll almost exclusively be interested in finite groups, decide whether they're isomorphic. This problem in some sense goes back even before we had a formal definition of algorithms, when Max Dane was trying to prove that the left and right-handed trefoil knots could not be continuously deformed to one another. And his method of proof that he eventually succeeded in was to look at the fundamental group of the complements, which are clearly isomorphic, but to actually look at what the isomorphisms were and to show that there's no orientation reversing isomorphism. So this problem goes back quite a ways, has lots of applications. Today, of course, we have computer algebra systems like GAP and Magma, where if you come across a group in your research, you can try and find out if it's isomorphic to some group that perhaps you are more familiar with. It's also of theoretical interest for its relationship to graph isomorphism. And here we have to talk about how the groups are given to you. So when the group is given to you by the full multiplication table, this isomorphism problem reduces to graph isomorphism. But when the group is given to you in a more realistic model from the point of view of a computer algebra system, say by a generating set of permutations or a generating set of matrices over a finite field, graph isomorphism now reduces to the isomorphism problem for groups in either of those models. Nonetheless, although the table model is not particularly practical from the point of view of computer algebra systems, it's still interesting theoretically. You can think of this as special cases of graph isomorphism that seem to be hard. And indeed, the running times are quite close. So the best we know for group isomorphism is 2 to the log g squared time, where g is the order of the group. And thanks to Babai's result of a few years ago, for graph isomorphism, we know 2 to the log n cubed time for graph isomorphism. And so group isomorphism really is a pretty salient obstacle to further improvements in graph isomorphism. And in particular, if you want to know if graph isomorphism is in P, that would imply that group isomorphism is in P, which we still don't know. It's also worth mentioning, particularly because we're going to be focusing on groups given by a generating set of matrices for most of this talk, that even in these more succinct models, the best running time we know is actually still the same 2 to the order of the log of the group squared time. Now, the input size here is much more succinct. It can be log the order of the group. And so as a function of the input size n, this running time is like exponential in n squared. But as a function of the order of the group, it's the same. Okay, so graph isomorphism is sandwiched in between these different flavors of group isomorphism. And so if you're interested in graph isomorphism, you might also be interested in group isomorphism. Now, in graph isomorphism, we know quite a lot. And part of that is because we have nice gadgets. So for example, we know that the decision version of graph isomorphism, tell me whether two graphs are isomorphic, is equivalent to the counting version, tell me how many isomorphisms there are, or the search version, find an isomorphism if there is one. These results are due to Mathon from 79. Also, we know lots of classes of graphs where the isomorphism problem in that restricted graph is equivalent to the general graph isomorphism problem. And again, these go by using gadgets. So what do these gadgets look like? Well, let's just as an example, look at the gadget for search to decision. So say I want to know if these two graphs G and H are isomorphic. Well, if they are, then this vertex has to go somewhere. So I want to add a gadget that somehow singles out this vertex. And one of the simplest things you can do is simply add n plus 1 vertices here so that this vertex now has the unique highest degree. And then for each vertex in H, I will try to add the same gadget. And the point being, once I do that, an isomorphism from G1 to H1, if there is one, which the decision oracle can tell me, must send this vertex, which had the gadget added, to this vertex, which had the gadget added. So if the decision oracle says, yes, there is such an isomorphism, you know there's an isomorphism that sends this one to this one. And then you can proceed and say, okay, now where does this one go? And I'm now going to add a bigger gadget with, say, n plus 2 vertices, and so on. And you could ask, in the context of group isomorphism, do you have the same thing? And in fact, Arvind and Taran in 2005 did ask this. They asked whether there's a search to decision reduction for group isomorphism. They also asked for ring isomorphism. It's also fairly natural to ask about a counting to decision reduction. as similar gadgets are used in the graph isomorphism case. And part of the issue in group isomorphism is that it seems to be very tricky to add gadgets and still get a group. Graphs are somehow seem to be much more flexible, where you just add on vertices and edges how you want. And with a group, you can't just kind of add on elements however you want and hope to still get a group. The other set of results that we get here from gadgets is reductions between different classes of graphs. And here the gadgets are slightly different, but again, they all take advantage of sort of the flexibility in graphs. And so you could ask the same in group isomorphism. Are there classes of groups where the isomorphism problem in that restricted class is as hard as the general isomorphism problem? Which brings us to the question of what are the hardest instances of group isomorphism? And here the hardest instances are widely believed to be groups with the following structure. When you mod out by the center, what's left is abelian, and every element has order p for some odd prime p. You can also do this when p is 2, but then the exponent here should be 4 instead of p. And these are called nilpotent groups of class 2 and exponent p. Why do we believe these are the hardest cases? Well, there are lots of reasons to believe this. But one thing to note is missing from this list is there's no reduction. There's no formal reduction known the way there is in graph isomorphism. And again, this comes down to this issue of it's sort of hard to use gadgets in the context of group isomorphism. Okay, so these are the questions that sort of keep us awake at night. Is there a search to decision reduction for group isomorphism? Is there a counting decision reduction? And are there reductions to hard instances, say nilpotent groups of class 2 and exponent p? And in our results, we make progress on all 3 of these. So for brevity, I'll let this curly h denote the class of p groups of exponent p and nilpotency class 2. And now p is going to be an odd prime. And all of our theorems are going to be in this model where the input is given not just by generating matrices, but by generating matrices over a finite field of characteristic p, where this p is the same as this p. So for question 1, for search to decision, we indeed get search to decision within this class of groups in time polynomial in the order of the group. For counting to decision, we also get counting to decision within this hardest class of groups in polynomial time in the order of the group, but now with a randomized algorithm. And we also need to assume that p is large. And finally, for reduction to hard instances, one thing to note is that not only did we not know a class of groups where the isomorphism problem in that restricted class was as hard as the general isomorphism problem, but for this class H, p groups of class 2 and exponent p, we didn't have a reduction to that class from any larger class of groups. To phrase this next result, I need to tell you a little bit more about nilpotent groups. So a group G is nilpotent if it's abelian, or if when you mod out by the center, what's left is nilpotent. Okay, so a group of nilpotency class 2 is the same thing as saying it's not abelian, but when you mod out by the center, it's abelian. Nilpotency class 3 is it's not nilpotency class 2, but when you mod out by the center, it is nilpotency class 2, and so on. And because each time you mod out by the center, you divide out the order of the group by at least a factor of p, the maximum nilpotency class here is logarithmic in the order of the group. Okay, so our final result here, reduction to nilpotent groups of class 2 and exponent p, we get a reduction to that class from p groups of exponent p and small class, so class less than p. And here, this reduction is now really polynomial time in the input size, right? So if my input consists of m matrices that are each n by n over a field of order p to the e, the input size here is polynomial in n, m, and log p to the e. And so this reduction is polynomial time in that. This may now raise the question for you of, well, we said that theorems 1 and 2 were also in this model by generating matrices, but we're reporting the runtime here as polynomial in the order of the group. So what is the real running time here? So let's say we have groups of order p to the n given by generating matrices over the finite field fp, right? So polynomial in the order of the group is like p to the o of n, which seems bad. It seems like it's simply exponential, and we're sort of used to that being brute force. But two things. First, group isomorphism in this class, as I mentioned before, in the worst case is still only known to be solvable in g to the log g time, which is like p to the n squared time, even when the groups are given by matrices. And so this running time, polynomial in the order of g, or p to the o of n, is really negligible compared to the running time of the best known isomorphism algorithms. The other way to think about it is the current best witness size we know for isomorphism in this class of groups is if the group has order p to the n, it's roughly n squared. And so a running time of p to the o of n is really only square root exponential in sort of the natural witness size. So this is sort of analogous to if you said you had an algorithm for satisfiability of n variable equations in 2 to the root n time. And these are the running times that we get for our first two reductions, the search to decision and counting to decision reduction. All right, so now I want to spend most of the talk telling you about the techniques that go into these proofs. Okay. The key stepping stone here, the sort of starting point for us, was the Baire correspondence, which goes back to Baire in 1938, which is a bijective isomorphism respecting correspondence between the kind of groups we're looking at. So groups where the group mod its center is abelian and every element has order p. So that means the center must be z mod p to some power, and the group mod its center must also be z mod p to some power. So the Baire correspondence gives a correspondence between such groups, and linear spaces of matrices over fp, where the matrices are n by n, where this n is the same as this n. So this is the dimension of G mod its center. And the dimension of the space of matrices you're looking at is M, where M here is the dimension of the center. Okay. Alternating here is convenient because it lets things work a little better in characteristic 2. But when the characteristic is not 2, this is the same as saying skew symmetric. And so if you like, you can just think skew symmetric matrices, but some of our results will also hold in the more general setting of alternating matrices, even when the characteristic is 2. All right, so I said this correspondence is isomorphism respecting, and we know what isomorphism means for groups. What do we mean by the notion of isomorphism for alternating matrix spaces? And the decision problem here is what's called alternating matrix space isometry, or sometimes pseudo-isometry. So the input is two lists of alternating matrices, each with D matrices in them, each matrix n by n. And the question is there an invertible matrix X such that when I replace each AI by X AI X transpose, and then I take the matrix space, which is the span of these matrices, that's the same as the matrix space, which is the span of the BIs. Okay, so here is that same problem again. And equivalently, if instead of saying span, I could say not just is there an invertible n by n matrix X, but also an invertible d by d matrix Y, where this matrix Y is affecting this span. So we say each Bj is some linear combination of the AIs, and these linear combinations should be invertible, right? That's the same as saying that these two spans are equal. All right, and so what we get is that this problem from the Baire correspondence is equivalent to testing isomorphism of P groups of nilpotency class 2 and exponent P, where the input P group is given by matrices over FP. And so actually all of our results are going to be phrased in terms of alternating matrix space isometry. And part of the reason for this is that alternating matrix spaces you can view as tensors. So instead of thinking I have D n by n matrices, I'm going to put them together as slices in a block like this and think of it as a 3D block like this. And now when I think of 3D blocks of numbers, it's a lot easier for me to think about how to construct gadgets. And then the point is, as long as this 3D block that I build with gadgets respects this skew symmetry property or alternating property, then I know from the Baire correspondence that I can go back to groups. So in principle, you could have done everything I'm about to tell you entirely in the group setting. But this was the way we came to it, was we realized this equivalence in terms of these tensors, and then that gave us sort of the flexibility in our thinking to construct the gadgets we needed. So I want to tell you a little bit more about the gadgets. The first gadget is you can add identity matrices like this, where they're going sort of, this one is in the first row, but it's behind my original thing A. This one is in the next row and further behind that. And then similarly, to keep it alternating, I also have to add minus the identity matrices down here. This gadget has the effect of restricting the change of basis X to be monomial, meaning it's allowed to, instead of doing arbitrary change of basis on the rows and then the same one to the columns, now it's only allowed to permute the rows and scale them, and then does the same thing to the columns. Okay. And this is actually what's going to let us get our first theorem. So this is the same as our search to decision reduction, but now phrased in terms of alternating matrix spaces instead of P groups. So for an m-dimensional alternating matrix spaces of n by n matrices over FQ, we get a search to decision reduction in Q to the n plus m time. And here's the outline of the reduction. So say you have a decision oracle that will tell you if two such alternating matrix spaces are isometric. First, you guess the first column of the isometry. You can do this by brute force in Q to the O of n time, because the first column is just a length n vector. So there are Q to the n of these. Okay. And now we want to somehow use the decision oracle to know, were we right? This is just like in the graph case where you tried all possibilities for where one vertex went, and you use the decision oracle to tell you if one of those was actually possible in an isomorphism. So we add our monomial gadget from the previous slide to fix the first column up to scale. And then we ask the decision oracle. We say, okay, now that I've guessed my first column and I've added this gadget, are the resulting things isometric? If they are, we guessed right and we continue. And now we have to guess the next column and so on. After we've guessed k columns, we add this monomial gadget on the first k rows and columns, right? Because the idea is we've actually guessed those. Now, we could have guessed them in the wrong order, so we could permute them. And then to guess the next column, again, there's just a Q to the O of n factor here. Okay. Now, there are a few additional ingredients that go into this. One is, in addition to the monomial gadget on the first k columns, we need an additional gadget to separate the first k columns from the remaining n minus k. Because without that, we sort of don't know if an isometry could mix those up, even though within the first k, it's restricted to be monomial. And the second thing is, at the end of all of this, we've guessed vectors, but we could have been wrong up to a monomial transformation because our gadgets still allow monomial transformations. So the final step is to solve alternating matrix space monomial isometry, meaning is there an isometry X, which is a product of a permutation matrix and a diagonal matrix, and this we solve in Q to the O of n plus n time. Now I want to tell you about the gadgets for our next result, the counting to decision reduction. And again, this will be phrased in terms of alternating matrix spaces. So it's analogous to the counting to decision reduction for graph isomorphism. So in graph isomorphism, you would pick some vertex v0, find out how many different vertices it can map to under automorphisms. Then find out for the next vertex v1, how many vertices can it go to under automorphisms that fix v0, and so on, where the ith iteration of this is you find out how many places vi can go under automorphisms that fix the previous I vertices. And then the size of the automorphism group of G will be the product of all of these numbers. And this will be equal to the number of isomorphisms between G and H whenever that number is non-zero. Okay. And so now, in the setting of alternating matrix spaces, instead of restricting to monomial matrices, which still allow permutations, we need to actually be able to test, for a given vector, where can it go? Which means we could allow scaling, but we really don't want to allow permutations, right? We want the analog of being able to fix a list of I vectors without permuting them. Okay, so beyond restricting to monomial matrices, we need to be able to restrict to diagonal matrices. So the idea is sort of similar. You start with the same gadget, but now when we had identity matrices here, you could permute these rows, right? Because if you permuted these, you could permute these back and forth and move them around. So to restrict to diagonal matrices instead of just monomial matrices, we now want to replace these identity gadgets with some other gadget that can't be permuted amongst themselves. Okay, and this is where the randomness comes in. It will be some matrix, and part of that matrix will be randomized. So the randomized analysis itself requires several ingredients, one of which is that the prime be large. This may be removable with sort of a tighter analysis here. And the other is a result from 1990 of Cantor and Lubatsky on the probability that two random matrices in SLN don't generate the whole group. Okay. And then these are sort of the two big things that we need, but a lot goes into this randomized analysis to show that the randomized construction we have actually does this thing of restricting to the diagonal subgroup. All right, and then finally, for our third theorem, which is reducing isomorphism from p groups of class less than p and exponent p to p groups of class 2 and exponent p. Here it's a little bit different. It goes a little bit more directly through the tensors. And so there are several gadgets that get used here, but most of these reductions were done previously. So the proof outline here is there's something called the Lazard correspondence, which generalizes the Baire correspondence and says essentially that for p groups of class less than p and exponent p, that group isomorphism there is actually equivalent to isomorphism of corresponding Lie algebras, which is now a linear algebraic tensor type question. So the next step is to reduce from Lie algebra isomorphism to 3 tensor isomorphism using a reduction of Futorny, myself, and Sergeychuk from 2019, to then reduce from 3 tensor isomorphism to alternating matrix space isometry from a paper of myself and Yoming Chow at ITCS 21, and then use Baire correspondence to go back from alternating matrix space isometry to group isomorphism, but now in groups of class 2. Okay. So to summarize, we started with these 3 questions, all of which have analogs in the graph case and where we know them in the graph case, and they're solved using gadgets. By translating from p groups to alternating matrix spaces or tensors, we gain some flexibility in how to build gadgets. So we built gadgets that allow us to restrict to the monomial group, to the diagonal subgroup, and the previous reductions for our third theorem use gadgets for sort of related purposes. And on all 3 of these questions, search to decision, counting to decision, and reduction to hard instances, we make progress using this viewpoint of tensors. And finally, just some open questions. Some are obvious, like a search or counting to decision reduction for larger classes of groups, ideally for all groups for the general group isomorphism problem. Can we reduce group isomorphism for even larger classes of groups to that for p groups of class 2 and really prove by a reduction that these are indeed the hardest cases of group isomorphism? One question is to de-randomize our counting to decision reduction. So in order to restrict to the diagonal subgroup, currently we still seem to need that randomness. We can check efficiently after you make your random choices whether the matrices you built satisfy the properties we need, but it would be nice to get rid of that randomness in the construction itself. And then there's also the interesting question of dropping the restriction of exponent p. What if we allow the group elements to say have exponent p squared, order p squared instead of order p? And here you can still do some of these translations, but it seems to lead you to alternating matrix spaces or tensors, but now instead of over the field fp or fq, over the ring, the integer is mod p to the k. All right, and there are plenty of other open questions that we mentioned in the paper, and I will stop there. Thanks very much.